Testing. 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 All right, we're live. Welcome to another Hoopo stream. Today we're going to be continuing on with our fine-tuning of segment anything. So segment anything is a paper that we read last week. This is a segmentation foundation model coming out of Meta AI Research. And over the weekend, I basically put together a version of the Scroll Prize training script. So the Scroll Prize is a competition we've been doing on this channel. And I basically adapted the training script we have there, except now it uses the segment anything model. And we're going to basically try to fine-tune this for the Scroll Prize. So unfortunately, or fortunately for us, depending on how you want to look at it, the Scroll Prize is very unique. It's a very interesting kind of obscure data modality, right? Because obviously the segment anything model is trained on basically cell phone images, right? 3-channel RGB images that have kind of an object-centric bias. But the Scroll Prize is a little bit different. So this is what the Scroll Prize looks like. The Scroll Prize basically looks like this. It's these weird X-rays that are slices through a piece of an ancient scroll. And even though fundamentally what we want to do is segmentation, right? At the end, what we want is to basically take those images like that and then basically output a segmentation mask, like a binary segmentation mask, like this. It's a very challenging problem because this is what it looks like, right? It doesn't look like anything. It's very difficult. And it's also not entirely clear how to even do this, right? So you have like 65 different slices. Do you run the segmenter on every single slice? Do you run it on random tuples of slices? Do you do any filtering on the slices? So there's a lot of problems around the actual data modality that we still have yet to figure out. But in the meantime, I figured, hey, it's going to be very hard to get it to work on that. So why don't we actually try to get it to work on this, the infrared image? Because the infrared image, segmenting this is actually very easy. And it's the same, it matches the modality used in the segment anything, right? This is just a 3-channel RGB image. I think this is actually grayscale, but you can make it RGB. So that's going to kind of be the toy problem that we're doing, right? So we're going to fine-tune it and get it to work on this toy problem, and then we're going to switch the images with the X-rays and see if we can learn something there. So maybe the real meat of kind of what I'm doing here is this part here. And you can find this repo on the internet. It's called Hoopo Ash and Venus. So all the code is in there. If you want to follow along, if you want to adapt it and use it, and you have your own technique, feel free, go ahead, MIT license, go ahead and use it. So basically the segment everything model has 3 parts to it. It has basically this image encoder here, which is this green brick. It has a prompt encoder right here, which is this purple brick, also includes this convolution here. And then it has a mask decoder, which is this orange brick here. So the image encoder takes your image, or really a batch of images, right? And then it outputs those images as embeddings, right? So it embeds them. It converts them from 3-channel RGB images into 256-channel encoded images, which are 64 by 64. And then the prompt encoder takes some permutation of either masks, points, boxes, or text. So Obviously, the most impressive part of their paper was the fact that you could feed the prompt via text, but in our scroll prize, really the ones that make the most sense for us are basically the points, the masks, and potentially boxes. Ideally, I'd like to not use boxes. I'd like to kind of get away with not using the boxes, but that's the prompt encoder. And you can think of the prompt encoder and the mask decoder as kind of these two little AIs that are talking to each other, right? So the prompt encoder, it receives your prompts, which are a bunch of points, and it says, how can I take what these points are, this points, this box, this text, and turn it into basically a language that the mask decoder can understand. And then the mask decoder listens to what the prompt encoder is telling it, and then gives you the actual masks. So the mask decoder is taking these embeddings coming out of the prompt encoder, which are basically, you have sparse ones, which correspond to the points, and then dense ones, which correspond to the masks. And then it uses them to give you the actual mask. So you have the low-res mask and IOU prediction. So IOU prediction is kind of like a confidence score. It's the model telling you how confident am I about this score. So in the paper, I think we go down to the actual training. And this is one thing that makes this a little bit complicated, is that they train this model in different ways, right? They train this model iteratively, first with kind of a supervised learning paradigm on existing data sets, then they trained it on, they used it for auto labeling. So this model is kind of like a bunch of different kind of modules that like have been trained not all at the same time with the same objective, right? So when we're going to fine tune this, there's going to be a similar kind of approach, right? We're not just going to fine tune the entire thing at the same time. And the way that the training was done, let me see here, the loss. So the loss that they're using is basically a combination of the focal loss and the dice loss. And then they also have a IOU prediction head trained with the mean squared error between the IOU prediction and the predicted masks IOU. So I'm going to be doing this part as well. So I made a loss here, which I'm calling combined loss. Yeah. And this loss is a combination of an MSE loss between the predicted IOU and the actual IOU. So that'll train the model, the IOU score, which is basically like a confidence. How confident is it about this mask? And then I'm also going to be doing a binary cross entropy with the logits loss, because the mask that comes out of the decoder is basically in logits form. So because all of our masks are binary, because this particular problem happens to be a binary segmentation problem. So that's the loss. So we have the main training loop, we have the loss, we have the data set, and yeah, now what we're going to be doing today is debugging this, right? So I'm going to run this. It's going to run into all kinds of errors. We're going to try to figure out what these errors are, and then maybe we do some of these to-dos and see where we are at. So let's get to it. Go here. Out of some of these. Run it. Let me full screen this too. It's a little bit bigger. Okay, so we're stopping here. What I did is stop here. I think it's just a breakpoint. So let's keep going. All right, here we go. First error. Index 2 is out of bounds for dimension 0 with size 2. So we have our point labels. Point labels here, we hover over that. It's an int64 of size 64. Okay, that seems like it should be right. Point labels of I equals self.labels. Self.labels is the actual ground truth mask, basically. and it's a uint8. Okay, I see what the error here is. So the error here is that this points should be like that. Okay. Let's run it. Got some yerba mate here. Alright, it's still not liking this. Can't convert foo to 0 to type tensor to numpy. Use tensor.cpu to copy first. Okay, so it's not liking that this point labels here is a tensor, right? But this labels is a numpy. So what we're gonna do is we're gonna make this a numpy np.0. np.int64, or actually no, uint8. Let's get real here. This is either only going to be 0 or 1. For I points in enumerate points. Let's also bring this down. I think we don't need to convert this into a numpy vector until afterwards, much like this one. So let's do that as well. Torch.from numpy of point labels to device. All right, let's run it. Okay. Let's make sure we have point is 64 by 2. Points. What about point labels? Is that at least the right size? So this is 64. Yeah, so the problem here is that this needs to be like this. Points of I0, or point of I0, sorry. And, or no, points of I0, sorry, yeah. This is what most of today is going to be, by the way. It's just going to be sitting here and getting all the dimensions right on all this math. Let's run this again. All right. Slices, ellipses, rewrites. Maybe we don't need to do that. Let's go back. Let's go back. I think we had the right idea to begin with. It was this. It was just off by 1 index is basically what the error was. .06, is that? Yeah, so the problem here is that this is in normalized coordinates. We need this to be in the crop, so in pixel coordinates. So we need to convert this point grid into pixel coordinates. But this point grid, this is taken from the SAM repo, right? So if the SAM repo, let's see where else this is used. Points by layer, generates point grid, append points by layer. Where's this called? Okay, that's no good. So basically the problem is that this is 0 to 1, but you can't use that to get the label. So let's do this. Convert points to pixel space. Look at that. Copilot already knows what we need to do. Point 0 is int of np clip 0.0 times self crop size 0 plus start 0, 0. To 65. I don't think you need to clip this. I think casting it to an int should be more than fine. So let's do this. Let's do 0.1. And let's do that. So actually we can probably move, definitely move this into there and not do this intermediate step here. On my Windows computer here, so like my shortcuts are different and it's it's bothering me for sure. Holy shit. How does anybody develop on Windows? I don't know. Right? Do you guys develop on Windows? Any Windows devs here? All right. Cool. Now we have gotten past that point, and now we're here. So this is as soon as it comes out of the data loader. So it our data loader object basically returns a bunch of information here. It returns images, points, point labels, low res labels, and labels. And it's complaining here. Cannot pin torch CUDA float tensor, only dense CPU tensors can be pinned. So it doesn't like this pin memory. So let's get rid of that for now. Pinning the memory on the data loader makes it basically faster. Windows bothers me for sure, yeah. But it can, I think it's not liking that some of these are basically not pinnable. Generally, the stuff you want to pin, I think there's too much crap here is basically the problem. So let's not worry about speed for now, and let's just run it as is without the memory pinning. Oh, the computer's freezing. So that means it's working. We might actually get a CUDA out of memory error. It's kind of smelling like a CUDA out of memory error. Yeah. CUDA out of memory tried to allocate 3.75 gigabytes. Okay, this is unfortunate because I think we're already using the smallest model. So, all right. What are we gonna do? So what we're gonna do is we're going to use the CPU for now. We're gonna use the CPU while we're streaming, because or else this is going to freeze the computer and you guys are not going to be able to actually see anything. So we're going to be using the CPU. Obviously you don't want to train on the CPU, but you can debug on the CPU perfectly fine. Let's also go ahead and make sure that our batch size is small. Let's try a batch size of 2. Or maybe batch size of 3. How about that? Okay, it's running. It's working. It's doing its thing. So, I mean, if this doesn't error out, we're going to have to inspect, because, you know, if you write a bunch of code and you run it and it works perfectly on the first time, that's actually not a good thing, because it's basically, you're probably doing something wrong. So we're going to have to figure out what's going on if it doesn't error out. Okay, so here we go. Forward missing 2 required positional arguments, boxes, and masks. Okay, so let's first check the dimensionality of these. So if I hover over points, I see here this is a float 64 of dimension 3, which is our batch. And this is a little tip here. When you're debugging, choose a batch dimension that is like weird, like 5 or 7 or something like that, because by making it weird, you can always recognize it, right? If we had a batch size of 2, then it can get confusing, right? Because then it's like, okay, well, is this being correctly batched? Is this being incorrectly batched? So if you choose a weird batch size when you're debugging, it makes it more obvious whether your batch dimensions are correct, because it has to be that exact weird size. So you have 64 points here, which is 8 by 8, right? We have an 8 by 8 grid of points. So 64 makes sense. 2, because they're 2-dimensional, right? X, Y. It's a pixel space. And 3, which is our batch dimension. So the points looks correct. Let's look at the points labels. That should basically match very closely. You have a uint 8, it's correct. The labels are basically either 0 or 1. You have 3, which is our batch dimension, and then you have 64, which is the number of points. So that also seems correct. So the prompt encoder, right, in the paper, let me do this rather than side by side. I think when I do side by side, it's too small for you guys to see, so I'm going to kind of alt tab a little bit here. But let's go up, up. Here we go. So the prompt encoder here, right, we're feeding it the points and the point labels, but then it also wants box and mask. We don't have text, and that's fine. You can not give it the text, but it wants one of these. Or it doesn't actually need them. So really, I think what it's complaining about is that they're not none. I think you have to do this. You have to say boxes equals none and masks equals none. Go ahead and run that. Okay, so one thing about this though is that without the boxes and the masks, we're really only getting the sparse embeddings. So this part here, the dense embeddings, is going to be empty. So I don't know if that's going to be good, right? Because I think the way that the masks are fed into the prompt encoder, the only time that it does that, right? Consider 2 sets of prompts: sparse, which are the points, boxes, and text, and then dense, which are the masks. Dense prompts are embedded using convolutions. Embedded just basically downsampled there. All right, where are we running into here? The size of the tensor 9 must match the size of the tensor 0. Okay, so we're inside the mask decoder. So the mask decoder is trying to predict the masks, and it has received the sparse prompt embeddings, right? The sparse prompt embeddings, which are a float 32 of size 3 by 65 by 256. 65 feels a little weird. I don't know why. That doesn't look correct. And then you have your dense embeddings, which are 3 by 256 by 64 by 64. So the image embeddings are 3 by 256 by 64 by 64, right? Which means that this here is 9 by 256 by 64 by 64, and it's trying to add that to the dense prompt, which is 3 by 256 by 64 by 64. So you see how there's a mismatch there. There's 9 things here in the batch dimension, and there's only 3 things here in the batch dimension. Okay. So let's close out. Let's go here. And we know that it's basically happening here, right before the mask decoder. So let's put a little breakpoint, and then we'll run our debug again, and that'll interrupt us right before this. All right. What happened here? Index 5319 is out of bound. Okay, I think this is wrong. I think this needs to be like this. Right, we need to typecast it to an int and then add it. Yeah. Needs to happen. Index 5299. Okay. It's really not liking this. So what is crop size? It's 1024 by 1024. This is 1024 by 1024. Let's see what's going on here. This needs to be 1 and 2. Because our crop size, the first element of crop size is the depth. Oh my god, come on. 1024 by 1024, 1024 by 1024, 0.0 is 0.0625, 0.0625, start, 0, this also needs to be 1 and 2. It's working, and it's probably going to open us up here in our breakpoint, which should be somewhere down here. It's going to pop us up right here. See how much longer this takes on the CPU. All right. So we're here. We're right before we go into the mask decoder, and we can actually check out what all the different things we're going to be feeding into this are. So the images, let's make sure that is correct. The images that we gave it are 3 by 3 by 1024 by 1024. That seems correct, right? It's a 1024 by 1024 height width. The channel dimension is 3, and then the batch size is 3. And once you actually encode them and they become image embeddings, you have 3 by 256 by 64 by 64, which is also correct, right? The embedded images are 64 by 64. They have 256 channels, and there's 3 of them because there's a batch of 3. Okay, the prompt encoder is receiving points at 364.2, point labels here, point labels, which are 3 by 64, and it's outputting dense embeddings. There are 3, 256, 64, 64, and sparse embeddings. which are 365, 256. This is the part that's no good, right? Because there's only 64 points. So why is there 65 dimensions in the sparse embeddings? Right? It should only be 64. That's the first thing that's weird. So let's go into this prompt encoder. So we can go into the build SAM, and then this is the prompt encoder here. Spatial size of the image embedding. Input image size. This is the part here. So we're passing it points. Points is a tuple of torch tensor or torch tensor with shape B times N times embed dim. So that seems fine. And then the dense embeddings should be B times embed dim times embed H and embed W. So the last dimension of the sparse should match the second dimension of the dense. Let's go ahead and see if that's the case. The last dimension of the dense is the last dimension of the sparse. So the last dimension of the sparse is 256, that's correct. Right, embed dimension is 256. And the second dimension of the dense should match that. So the second dimension of the dense should match that, 256, it does match. Okay, so maybe it's not these. Maybe it's not the sparse and the dense embeddings. Maybe it's the image embeddings, right? So let's go into our mask decoder and look at the documentation there, see what we get, see what we find. So we have image embeddings, sparse prompt, and dense prompt, which basically just calls this predict mask. Let's look at that. Image embeddings, HP, sparse prompt. Okay, so there's no documentation here on what the size of this needs to be. So one thing I'm going to try here is I'm going to try to pass in these masks. Let's go ahead and do this. And let's comment that out. Let's pass in the masks, see if that fixes the situation. It might just cause the prompt encoder to error out. Okay, it's thinking. And while that's thinking, let's open up the segment anything. One of the notebooks. Input type unsigned char and bias type float. Okay, so it doesn't like the fact that these masks are uint ain'ts. So we need to figure out what the actual inputs and outputs to these things are supposed to be. So let's open up one of the examples that comes with the segment anything. So I think they have some notebooks. Let's open up that, and they have a automatic mask generator example. Let's open up that. So this is an example where they're just running some stuff here. Let's go ahead and do this. And let's put breakpoints in these. So let's go into the prompt encoder. Or actually, I think we can put breakpoints in the actual generate call. Automatic mask generator, mask generator.gen. Let's select the kernel here. Let's use this one. Go into this call here. And generate masks. Generate crop boxes. It's not what we want. In mask, post process, current annotations, generate crop boxes, crop length, uncrop. At some point it has to run the prediction on the actual model, right? Here we go. Self.predictor is a SAM predictor. So inside the SAM predictor, this is where we want to put our breakpoint. So let's put a breakpoint here. Right here. Right at when it predicts, and right here. These are the two that we want to care about. Okay. So now that we have our breakpoint set, let's go ahead and run this notebook. So I think we need to run this. Actually, can we just run all of this? No, we can't. Run that. This is empty because this is not a Windows path. We need to make this a Windows path. Okay. Now it works. Let's actually go into our predictor. I don't think we can do debug like that. Let's do old school debugs. Or no, because we do want to be able to see it. Let's just see if it actually even works in Windows. Okay. Restart kernel. PLT is not defined. I have to import PLT here. Using collab false. Kernel has died. Ugh. What is going on, guys? What is going on here? Canceled future request. Run and debug. Execution count null is not defined. How do I debug a add configuration? Fast API. Is there a Jupyter notebook? Let's ask the internet. Jupyter Notebook debug configuration VS Code. This will run the cell in the debug session and will pause in your breakpoints. Okay. So I think all we have to do is just hit debug in that specific thing. Start. Clear all outputs. This is not the right path. Let's put a Windows path here. This is also no longer here. This is now in Ashen Venus. Let's load it. No such file or path. It's because this needs to be like that. VITB and VITB. And let's change the device to CPU. Okay, that's working fine. Okay, this is the one. Close out of this. Because we want to use this image here. Bring this image down, put it here, and let's call it image. And let's see. Let's execute above cells, run by line. I like run this. Debug console. Debug notebook. Jupyter debug cell. This is the one I want. Control Shift Alt Enter. A weird situation. All right, hopefully this runs into our breakpoints. All right, there we go. Okay, so this is what it's supposed to look like. So what does it supposed to look like? It's supposed to be a float 64 for the point coords. And the point labels are supposed to be int 32. So let's go ahead and change that. So up here, our points are supposed to be float 32 to torch float 32. Can you combine these? Let's ask GPT-4. Can you combine the 2.2 calls in this expression into a single call? Is it faster or slower? So I want to see if I can combine these. You can combine the do a single call by specifying both dtype and device. Combining the .to calls into a single call should be faster because it reduces the number of operations. Okay, that's all I need to hear. Just tell me what I want to hear. All right, so let's close out of that. And this one here, what did we say we wanted this one to be? Point labels. Point labels should be a int 32. Okay, so let's make this int 32. And let's also add a dtype here just to make sure that it's the right size. Okay, so our points and our point labels now match the correct data types that are used in the example. Let's make sure the sizes are correct. So the size of this here is 64 by 1 for the point labels, and then the point coordinate is 64 by 1 by 2. So if we go into our source, what do we get for points? Actually, let's write it down. So right here, let's start writing some of this down. Points is 64 by 1 by 2. Point labels is 64 by 1. So when we go back, we'll make sure that that's the case. Make sure 64 by 1 by 2. And this one here is 64 by 1. Okay. What about our boxes? So we don't have any boxes, right? Boxes is none, and masks is also none. So let's go back into our source and let's comment out that. So right here, let's also get rid of that, and let's have masks and boxes both be none. And let's get to the next point. Okay, so now we get to the next point, and let's see what our sparse and dense embeddings are. So our sparse embeddings are float 32s of 64 by 2 by 256. So right here, sparse embeddings should be a float 32 of 64. I'm already forgetting. I have a terrible memory. What is this? Float 32 of 64 by 2 by 256. 64 by 2 by 256. And our dense embeddings should be also a float 32 and a 64 by 256 by 64 by 64. 64 by 256 by 64 by 64. Okay. The other parts here that we need are the image embeddings. So what are the image embeddings in terms of dimension here? The image embeddings stored here as self.features are float 32s of 1 by 256 by 64 by 64. Also float 32, 1, 256, 64 by 64. Okay. So we can disconnect here. Go back to our automatic mask generator. This is still running. We don't actually really care. We can interrupt. Interrupting Jupyter kernel. On. Interrupting the kernel, timed out, restart. Okay. Oh no, the computer's frozen. Okay. Let's clear all of our outputs. And let's go back to our code here. So we have ideas of what these are supposed to be. Let's go and rerun this, and let's make sure that our things are the correct size. So let's put this here. Let's put a breakpoint right here, another breakpoint right there. Let's run it. Let's see where we're at. All right, it's thinking. Still thinking. I feel like we should reduce the batch size. You know? Okay. Points. Float 32, which is correct. Let's put that there. Float 32. Int 32. Point labels. 3 by 64. Okay, you see, this is no good. Point labels needs to be 64 by 1. And points is 3 by 64 by 2, also incorrect. So these are no good. So let's close out of this. And let's come back up to our data loader where we are creating these two tensors. And we need to change them. So point labels of I. We need to, why does this have 3 dimensions? Put a breakpoint here and let's run it. Not this, this one. Okay, so points here. 64 by 2. We need to unsqueeze this. Point dot unsqueeze. Ooh, not all caps. Unsqueeze, and we need to unsqueeze it in dimension 1. I think, right? 64 by 2, and we want it to be 64 by b by 2, yeah. Let's come back up here. Copy paste this here so we got a nice little reference. Okay, so unsqueezing it should give us that batch dimension in the middle. And point labels needs to be 64, comma. We also need to unsqueeze this. But the unsqueeze here, unsqueeze. also needs to happen like this. Okay. Close out of that. Clear this breakpoint. And run it. Go back down here. I think we might run into issues because the data loader is going to batch these things potentially incorrectly. Okay, let's run this. See what we got for points here. Yeah, you see the problem here is that this is not the right shape. The batch dimension was incorrectly assumed to be at 0. So we need to get the points and then do the unsqueezing. Okay. Change points from B64 2 to 64B2. And we also need change point labels from B64 to 64B, like that. Okay. Save, close out of this. Here, run it. We should hopefully get what we want. So something else that could be potentially different here is that we're getting these dimensions from the mask generator example, but the mask generator example does it once at one at a time. So the way that the batch dimension is used might be different in training. Oh yeah, we need to get rid of the unsqueezes up here. Close out of that. Let's rerun that. There's also this multi-mask output here. Which I feel like might be the way to do this. Okay, let's see. Let's make sure here we got points. is 64 by 3 by 2, which is correct. And then point labels, 64 by 3. All right, that is also correct. Let's go ahead and get to the next point. Okay. So now we should look at our sparse and our dense embeddings, and they should match this part right here, right? So let's make sure that it matches. What is our sparse embeddings? 64 by 4 by 256. That does not look correct. What about our dense embeddings? 64 by 256 by 64 by 64. 64 by 256 by 264 by 64. Okay, that looks correct. The dense embeddings looks fine. What about our image embeddings? Our image embeddings are 3 by 256 by 64 by 64, which is also correct. Okay, so the only one that's weird is the sparse embeddings. The sparse embeddings here where is this 4 coming from? Let's look at this paper a little bit. So, the automatic stage, I want the decoder, or the prompt encoder here. Sparse points and, okay. Sparse points coming in. Print anything, semi-automatic. I think they have a picture of the actual encoder that's better than this one. Let's minimize this a little bit so it's easier to find what we want. I think it's in the appendices, yeah, right here. Prompt encoder. Sparse prompts are mapped to a 256-dimensional vectorial embeddings as follows. A point is represented as the sum of a positional encoding and one of two learned embeddings that indicate if the point is either in the foreground or background. Oh, okay. I think I know what's going on. So the reason this was 64 by 2 by 256 is because this is 2 times b, and b was 1. So it actually makes sense that our sparse embeddings are 4 because our batch dimension should be 2, right? No. Still doesn't make sense. If we run this, yeah, we get, that's the error right there. Dense prompt embeddings, 64 by 256 by 64 by 64. And here, 192 by 256 by 64 by 64. Sixty-four by 5 by 256. 64 by 4 by 256. We're concatenating them, so now you have 9. 64 by 9 by 256. And you're repeatedly interleaving them with this one. Whoa. Whoa. What is going on? Ugh. This is not good, because it means that this this prompt encoder might not be correctly implemented to work with batches. It might just be only this is the mask encoder. Or the image encoder? No, I want the modeling prompt encoder, this one. Get the batch size of the output given the batch size of the input. See how here it's using the first element of the points as the batch size. So maybe we don't actually want this. Yeah, I think this is actually no good. We don't want to do this permute here. Let's come up here and let's maybe do the unsqueeze again. Let's try it without the unsqueeze, and then we'll try it with the unsqueeze, see what we get. While this runs, I'm gonna go real quick to the bathroom. I'll be back. We're back here. Now we have our dimensions, which we thought were wrong, but might not actually be wrong. 3 by 64, 3 by 2 by 64. Okay, let's keep going here. And let's see if, yeah, we get the same error. Okay, so now let's close out. Let's try it with the unsqueeze. Let's see if that does it. So we save the unsqueeze, and go and rerun it. So now we're going to try it with our unsqueezes. So it'll at least match the dimensionality of the example, but it's going to have the where is it? Mass generation. Nope. This one. Nope. This one. Self features. Sparse prompt. I think if we actually go to the SAM model. Oh, wait up. Okay, we're here. Points are now batched. 364.1.2. 364.1. Okay, it's issue with the points here. Tensors must have the same number of dimensions. Got 4 and 3. Padding point is points.shape0, so it wants the batch dimension. Okay, so this actually gives us a hint here, right? If padding point needs to be able to be concatenated with points, then we know that the dimensionality here, this is also where we get the 65, by the way. The dimensionality of this should have, there shouldn't be that unsqueeze there. This one here. However, we still don't know if we want the unsqueeze on the point labels. Yeah, so here you have labels torch.cat with padding label, and padding label here has the batch dimension and then 1. So we know that this should also not be unsqueeze. Okay, this is not looking good though, because we thought that unsqueeze might have actually been the reason. Should be B by 64, and this should be B by 64 by 2. Yeah. Embed the points. Forward with chords. Point labels equals 0, labels equals 1, and then labels equals -1. So 3 by 64 by 2, and 3 by 64. That works fine. This is, our sparse embeddings are still the issue here. right? This is what it was in the example, 64 by 2 by 256, but the ones that we are getting are just not that at all. They're 3 by 65 by 256, right? Like, what the fuck is that? 3 is the batch size. That seems fine. But where is that 2 coming from? Go back to our prompt encoder here. Prompt encoder. So when we embed the masks, we embed the boxes. The batch size is correct. When we do the forward, we get the batch size. The sparse embeddings is batch size by 0 by embedding dimension. If the points is none, which is what we're doing, we're using points. We're embedding the points, and then we're concatenating these sparse embeddings with the point embeddings. Okay, so it's adding these up. It's concatenating them on dimension 1. Okay, so this is maybe telling us what's going on here, right? If we have batch size 0 by 256, right? We have batch size by 0 by 256. So this is not batch size though. Yeah, there's no batch size here. I think that's the issue. Right, like the prompt encoder here is losing the batch size. Does the mask decoder, does the mask decoder have a batched version of the forward call that we should be using? So we have our masks, we embed the masks, we don't need it, and all it would do is it basically just reshapes the dense embeddings. So here, this is the mask decoder. No, this is the SAM predictor. Let's go to mask decoder. Right here, prompt encoder, we want segment anything, modeling, mask decoder. Predict mask. Is there a batched, ooh, forward. Predicts masks. let's see what these other calls look like. So Control-Shift-F mask decoder. Here in predictor.py, we have the mask decoder. Where is this predict torch? Mask input, multi-mask input. Get image embeddings, is image set, self features. That is correct. 3264. Dense embeddings. There's no batch dimension on the dense embeddings. Let's look for an unsqueeze here. Let's look at the SAM file. Segment anything, notebooks, models, SAM. Nope, not prompt encoder. Want segment anything, modeling, SAM. This one here. This is the one we want. See how this is unsqueezing in the 0th dimension here. And you see how this is actually provided images and prompts. Yeah, I think maybe we need this. We need this unsqueeze 0. Let's try that. Batched input. Points. I feel like here's where we should actually put breakpoints here. They're actually more interesting. Let's do that. Let's close out of that. Come here. Batched point prompts for this image, b by n by 2. Point labels, batched labels with shape b by n. That's correct. Batched mask inputs to the model, b by 1 by h by w. image 3HW. All right, let's run this. See what we get. Also, while we're doing this, we can actually, I have it set up so that TensorBoard is here too. Let's look at the TensorBoard. We need to run it, so let's go ahead and do that. Anaconda prompt. Come on, Anaconda prompt. CD documents, dev, Ashen, Venus, TensorBoard, logdir, output. Conda activate Ashen, Venus. Fuck. Is this the Anaconda prompt or is this like the command shell? What the fuck am I looking at here? Okay. CD documents dev Venus TensorBoard logdir of output. Okay, let's run it. So we're here. See what these look like now. All right, so we got past this somehow. 3 by 256 by 64 by 64, and then source. Three by 256 by 64 by 64. One by 3 by 256 by 64 by 64. Repeat, interleave. tokens.shape0, which in this case is the batch size. Expand per image data in batch direction to be per mask. Okay, so the problem here is I think this is just not intended to be batched. Let's do batch sizes of 1. I know that that's technically blasphemy here, but let's close out of that. Let's run it. This should not be unsqueeze. What do we have now? 1, 256, 64 by 64. 1 by 65 by 256. One by 256 by 64 by 64. We needed to get rid of that squeeze before we run this. Put a little to-do there just to figure out what exactly is going on here. But we just need to keep it moving, you know? All right, so we got past the decoder. It's outputting. We might be able to come here, hit refresh. Might have some images. We do not. Because we need to say log images true. We do want the images. All right, what is it failing on now? Dice score. The shape of the mask at index 0 does not match the shape of the index tensor at index 0. So our labels versus our predictions. Okay, so something's going on right before this. Let's see where we actually go ahead and do this. So low-res masks and labels. I think it's because this needs to be low-res labels. Like that. Let's clear some of these breakpoints here. let's run our sweep. And we should be getting images now. Keep this refreshed. Add images. Size of input tensor is format tensor shape 1 by 1024 by 1024. Okay, so this needs to actually also another unsqueeze. Oh shit. Weird. Unsqueeze 0. Labels. Zero, 1, 2, and 3. Yeah, we actually need to unsqueeze labels at the top. Here's what's going on. So here, when we create this labels, we need to unsqueeze it. So we need to do this up here. Labels equals torch from NumPy labels to torch float 32 and also unsqueeze 0. I think we also don't need this dot clone here. Okay. And then we can remove the unsqueeze from here. All right, let's go ahead and run this. Labels as type np uint 8. Okay, the problem is we need to do this not here, but below. So this line needs to move right here. All right, now let's save. I don't know if you guys can see, but Boo is sitting right there, being super adorable. All right. Point slice indices must be integers or none or have an index method. Point labels is 1 by 64 by 2. Point chords 1 by 64 by 2. Point image So the problem here is that height is 0.065. This is the same problem that we had before where the point chords were not in normalized or in pixel space. They're in So how come our points are not? Could that be the issue? Already transformed to the input frame of the model. What does this mean? Does this mean in pixel space? What's going on, Boo? Let's come up here. I think we need to convert our points into pixel space. Convert points into pixel space. Do that. Then that means we no longer need this because we can just do this. If the points are already in pixel space, then we can just evaluate. This needs to be an int. All right, now what's going on? Type error. Because points is a float. Good God. Okay, so we need to not typecast it here. Cast it here. 2 dtype equals, or as type, I think. As type np in 32. All right. Now we're here. Now our point labels are int32 and our point chords. Point chords are fucking floats. Means that the height and the width here need to be ints. All right, it's going. Let's see. Okay, so something is definitely wrong with our images. And also something's wrong with our points. Okay, hit the refresh. Okay. So what is wrong with our images? Image is that, and then from NumPy image, what up here? IR image. Let's out of this. Let's put a breakpoint here. Put a breakpoint here. I kind of want to rerun this because I want to see if these points here are decimals. What does this apply chords? Okay, so I see. These need to be in, not in the global image coordinates, but in the it needs to be like that. Get rid of this. But we still don't know what's going on with this image, so. Run it. Let's run it again. All right, we're here. What is our IR image? Our IR image is 6465 by 5249, and it's a float tensor, but everything is in 255, 255, so we need to divide it by 255.0. That'll make it a float. Our IR image now is float 32. That seems more like what we want. Rid of this debug. Keep going. Now it's 1024 by 1024. Those values seem more like what we want. Keep going. All right, this is what we want. You see? This is the infrared image. This is the correct segmentation mask. And this is the correct points. All right, we're doing good. Okay, the bad thing here, though, is you see how these points, these are not correct, right? Some of these points should be green to indicate that they're part of the thing. So let's go back. I'll interrupt this. Problem is that the point labels are incorrect. And why are the point labels incorrect? The point labels are incorrect because they need to have the start, right? They need to be relative to the entire image. So that should be what it's like. Wait for this to start going. It's going. Hit refresh here. Is this correct? That looks correct. Got this M. Do these points correspond to that? How come the points don't have all of them? Let's go to our visualization code here. So here where we're plotting the points, input points, set ID, phase, train step. Height minus point width, height plus point width, width minus point width. This is the part here. Labels.cpu.numpy. What is labels here? Times 255. this should be like that, right? Let's close out of that. We can actually look here. Let's see if the loss goes down. Combined loss. Why is this all grayed out? Custom scalars. It's not saving that. Okay, so this seems to be fine. Let's rerun this now that we have the point image. We should hopefully get the mask in the back. We could actually probably put a breakpoint there. Yeah, let's do that. Close out of that. Rerun that. So it should break us here, and we should get to see this. Labels is going to be 1 by 1 by 1024 by 1024. The values inside label are it might already be in 255, 255, 255. Can I get a min and a max here? Data. Data. Debug console. Can I go in here? Labels. Labels.min. Labels.max. Okay, so I don't actually need this 255 here. Let's go back here. Let's close out of this. Let's rerun that. Let's see. Let's see. Okay, run. Refresh. What do we got? Input labels. Input points. All right, you see this does work. Okay, we're doing good. You see, so this is the mask. And you can see how the points that are outside of the mask are red, and then the points that are inside the mask are green, showing that they're inside the mask. So this doesn't really match the paper because the sampling in the paper is actually a little bit more complicated. So they have a point sampling. Yeah, our default point sampling, first point is chosen deterministically as the point farthest from the object boundary. Each subsequent point is the farthest from the bounding of the error region between the ground truth and previous prediction, which is more complicated than what we have, right? We have basically just a grid. But really, I think what we want to move towards is something where there's a point like kind of right in the middle here, point right in the middle there, point right in the middle there, and so on. Kind of weird how this output mask just doesn't look like anything. I guess this is kind of a weird ass image anyways. Okay, let's clear this breakpoint. Let's run again. We should have one more in here. We should have a step 2 now. Yeah, step 2. Boom, boom. That seems correct. Input points. This also seems correct. and then output mask. The fact that this is just complete shite is a little weird. But okay. Save that. And now we wanted to see why isn't our loss getting written. So we have our loss name, phase, set postfix, add scalar, combined loss, train, -267, whatever. Why is this not? Okay, our loss is going down. No, little sanity check. Nor outliers, no smoothing. Fit. Okay, kind of want to see that. I don't like how big it is though. That's a little unsettling for sure. See this, how it's growing out of control. Step 2. Did it get something? Oh, loss going back up. That's not good. I think we just need to run this for longer. That's the question. Okay. So let's actually kill this. What I'm going to do is I'm going to go eat some brunch, and in the meantime, I'm going to okay. I actually have to run to another meeting as well. So I'm going to hit log images false here. I'm going to run this. And without the images, it should run faster, right? Because it doesn't have to save the images to TensorBoard. And then we will run this for a while and see if we actually get some good shit or whether it's just going to be a bunch of nonsense. So let's say debugging live sesh. We'll commit. Save to that. Sync changes. And yeah, see you guys tomorrow. Thanks for watching the stream.